All right, recording has started. We're learning about molecules, atoms, and chemistry. Okay, all right. Okay, I'll cut that out. So these four major terms, you have the molecule, which is the umbrella term for all of the bonded atoms that we see in nature. It includes any type of atom that is one or more, or two or more bound together. So two examples that I'll give, and which we've seen every day and we need to live, is H2O and O2. So H2O is obviously water, and O2 is oxygen gas. And it forms a diatomic gas. We'll learn about that more later on. So a molecule is everything. Now for compound, it's two or more elements chemically bound. That's a little bit different. So for a compound, it's basically like a molecule, but more specific. The bond has to be between two or more of different types of elements that are on the periodic table. So out of H2O and O2, which one would be just a compound? Yes.
H2O.
Good. So H2O is a compound because it has hydrogen and oxygen. They're both molecules, but H2O is a molecule and a compound, where O2 is not a compound. It's just a molecule because it has two or more of the same type of element. Okay, good. Now the next distinction that we need is atom versus element. So an atom is the smallest particle of one type of element. So an atom, you're talking about the literal particle. So I hear this phrase all the time, and it's wrong, where people say there's atoms on the periodic table. Your periodic table is probably made of a lot of atoms, but there's no atoms on the periodic table. There are elements on the periodic table. There's 118 of them. So an element is the type of atom on the periodic table. So that is the thing that we need to know. So if you have a sheet of aluminum foil, you can say the aluminum foil has millions and billions of atoms of the element aluminum. So aluminum is not an atom, it's an element. But you could have atoms of the element aluminum. So that's a very important distinction we need to get across before we delve into more detail with chemistry.
Stupid question, but what about hydrogen?
So hydrogen, well, so is hydrogen gas, which it naturally forms into H2. That's a molecule, and that is considered to be in its elemental form. The same thing with O2, F2, N2 for nitrogen. That's the most abundant gas, and those are molecules, and then they're in their elemental form. So yeah, so just hydrogen itself is an element. But if you're talking about hydrogen gas, that's a molecule, and if you're talking about a specific particle of hydrogen gas, that's two atoms of hydrogen bound together, making it a hydrogen molecule. So if that makes sense, yeah. Okay. All right, talked about that. You can split and do things to atoms. Oh, someone has a chat thing. Where's my cursor? There it is. Yes, I will be. Oh, so I will be recording and posting the lectures. So these lectures will be on YouTube, and I will render them. Since my screen is 4K, they will be rendered in 4K, 60 FPS. So those gamers out there, or video enthusiasts, I got you covered. Okay, that's why I hate this owl camera. It's in like 240p. All right, so what's next? All right, so here we go. The scientific method, very important. So the way any scientific discovery happens is a brilliant person, or maybe not so brilliant person, has an observation. You use your senses, your sight, your smell, your taste, your touch, and you have an observation. And we use Isaac Newton as an example with gravity. So he saw things every day fall down like that, and he was like, all right, why do they fall down? That's the key question. So it's very important to ask the right question, not just any questions, but the right questions. I mean, for you guys, you can ask any question because I'm here to help. But in developing science and discovering more for the scientific community, it's asking the right questions. So one of my advisors once told me that getting a PhD is getting the license to ask the right questions. And I really took that to heart because, and I'm starting to see it in my own growth of my education, where before I would just be like, all right, I got to know this material, I got to know this material, I got to know this material. But now I'm thinking, I don't really care about just knowing the information. I'm thinking why, or thinking of follow-up questions that nobody knows the answer to. Every follow-up question that nobody knows the answer to, that's a research project. That's a potential discovery. It's a potential publication. So it's important to think in this method or in this way of why and or how or why doesn't, or what about this? If you're going to be a scientist or even an engineer, that's how we make new inventions and innovations all the time, is from asking these questions. So very important. So the scientific method is the method of how these questions become discoveries. So the first thing you need is an observation. So Newton saw the pen drop or the apple drop, right? Then he made a hypothesis. So the hypothesis is an educated, a little bit more than an educated guess. People, and the way I learned it back in middle school, high school, and college, they're like, oh, a hypothesis is an educated guess. It's a little bit more than that. It's based on already previously known science. That what can this be based on what the scientific community knows already? But for Newton's case, it kind of was a guess because the scientific community wasn't really developed. But he's like, all right, it could be, I'll name two hypotheses right now. It could be there's some kind of force that the Earth is pulling the object to the ground. There could be an attractive force of electricity that is, let's say a charge. Let's say the Earth is positively charged and the object is negatively charged. That could be a reason why it hits the ground and sticks to the ground. It could be magnetism. It could be a giant cyclops monster that grabs the object with an invisible hand and brings it to the floor. It could be anything. These are all hypotheses in a new field. But then what you have to do is you have to test these hypotheses with an experiment, with one or more experiments. And usually those experiments are to rule out possibilities, not usually to prove something, but to prove against something. So you can, with those two that I just mentioned with magnetism and electricity, you could say, all right, I will get something in the scientific community that is known to be neutral. Let's say the helium atom is known to be very neutral and doesn't really react with anything. It is a noble gas. Get a block of helium. Solid helium is really difficult to find at very extreme pressures and temperatures, but for sake of argument, get a block of helium and drop it. Does it hit the ground? Yes. So you know that some kind of charge thing with gravity, that's not how it works. Then you can try to take something that has magnetism and doesn't have magnetism. They both drop. So it's not magnetism. Then you come to the conclusion, all right, there's some other force. Then Newton, what does he do? He does more experiments in the form of math. So he does mathematical equations, invents calculus. This guy invented calculus. You guys are taking Calc 1, I assume, right? This guy invented calculus. That blows my mind. He's probably the smartest person that's ever lived. So he does calculus equations, and he determines that, all right, there's this force that has this kind of attraction to massive objects have an attraction to smaller objects, or attract smaller objects. And then Einstein was like, oh, that's because it bends space-time. Duh, that makes sense now to us, but that's what gravity is. So it is this endless, well, not endless, but this reoccurring loop of observation, make a hypothesis, do an experiment, change your hypothesis, do another experiment, and then keep that going until you have a mountain of data, or you or other scientists have a mountain of data. That mountain of data that proves a specific point, it's called a theory. So a theory is a conglomerate of well thought out hypotheses that have been tested and proven to point in the same direction of outcome. And then that theory will eventually turn into a law. So we'll talk about that. So measurements, hypothesis, yeah, we talked about this already. Then they become a natural law. So like the law of gravity, or That's my jersey coming out. So law of conservation of mass, where mass cannot be created or destroyed in a closed system. So you can't just gain mass. I thought of a really funny joke that I'm not going to say. It has to do with, never mind. Nothing bad, nothing inappropriate, but it's just like not good for class jokes. I do have a chemistry joke though. So there's no one named Adam in this class, right? I don't think so. And if there is, I'm sorry, Adam. So why can't you trust anybody named Adam? Because they make up everything. Get it? Like atoms. Yeah, okay. All right, I'm done. Drop the mic, get out. All right, so you have a law. Then drawbacks, yes, science isn't perfect. You know what science that I think is the most imperfect? Probably psychology. Because what they try to account for is the human condition. And they try to make scientific conclusions on population. It's still, I mean, psychiatrists and psychologists and research psychologists and psychiatrists, that's an amazing job. That's something that, psychology is something that's interesting to everyone. So kudos to them. But I just think presently the science is so flawed because they're trying to do something that I think is almost impossible until they could quantify the human brain. They don't really know much about the brain yet. So they're trying to quantify the brain and generalize it amongst populations. And then they prescribe drugs based on that. So it's weird. It's a very difficult science. I think that science is more difficult than biochemistry. There's no placebo effect when it comes to cells. They're not going to react just because their body feels like, oh, I feel better now because I just have this preconceived idea that I feel better now. But anyway, let's get back to this. So which of the following is an example of a quantitative observation? So quantitative means it's a quantity. It talks about specific quantity rather than a qualitative observation, which is just a non-measured observation. So which one do you think? A, B, C, or D?
D.
Yes, D. The temperature of the water is 45 degrees Celsius. That is a quantitative observation. I know that for a fact because I measured it. But how accurately did you measure it? That's what we're going to talk about next. Oh, after the SI units. All right, that was almost a perfect segue. But so measurements in science, we use the SI units. So the SI units is the standard international unit of measurement, units of measurements. And there are base units for this. And it's based off the metric system, very similar. It's nowhere near the US system. The US system's all messed up. Feet, pounds, and inches and stuff. What's another? What's the slug? That's it. A slug is the US unit of mass. You think it's a pound. I'll talk about that in a minute. So mass is, the definition of mass is how much substance is in a specific object. Not how much it weighs, how much matter is in it. So you can quantify the mass by how many atoms of all the elements, add them up, find the molecular weight, and then do your math, and that would give you the mass. So that's a key characteristic. So mass, and also this is, I think there's slides with this on it, but you just write, and there's a slide with this, with what I'm saying. So, okay, another thing about how I lecture, I say a lot of stuff. You don't have to write everything down. It is on the slides, but you saw I talk about it first, then I kind of skip the slides that have the written information, because I don't know about you guys, but I hate when professors just mass, kilogram, and I just read off the slide. I can't do that. So this is the way I do it. So if you have any, and also I do go fast sometimes. So when we get into more intense stuff, if I'm going too fast, please let me know. And everybody online, just shout out, and I won't be disrespected because I'm here for you. Okay, so we have the kilogram. For length, we have the meter. For time, we have the second. For temperature, you may not have seen this one before. It's called Kelvin. So Kelvin is the standard absolute unit of temperature. By absolute, I mean that it starts at 0. And there is no such thing as negative Kelvin. Ooh, why not? So we'll talk about this more towards the end of class when we go over those slides. Then there's two where we're not really going to cover, which is electric current, which is in the ampere or the amp, and that's more in physics. Then we're not going to cover really luminosity, intensity with the candela. So, but we are going to talk about a hell of a lot is the amount of substance, which is the mole. So look at the nice job they did on abbreviating it. M-O-L-E, yeah, I'll take off the E, mole. So that's the mole. So if you know from, let's say you took high school chemistry, 6.022 times 10 to the 23rd, that is the Avogadro's number, meaning the number of particles that are in 1 mole of a substance. So we'll be learning all about that, how to do calculations with it, everything in chapters, I don't know, 2, 3, 4, maybe, or definitely. Okay, so with these units, since they are the standard international units and they work very similarly to the metric system, we have prefixes that we can use to either scale up these units or scale them down. By that I mean, if you have this desk, for example, you're not going to measure this desk in milligrams or even grams. You're going to, because you'll have hundreds of thousands of milligrams, thousands of grams. We're going to measure this desk in kilograms. It'll be like 20 or something, 30. That's even too heavy, maybe 15. So in order to scale up or scale down these numbers, to make them tangible and relatable to us and easy to work with mathematically, we need to understand these prefixes. So in blue are the ones that, these are the ones that you guys should be familiar with. Now, we'll start from the base unit and we'll go down and then we'll go back up. So I would say for chemistry, most of your focus should be on here, the down ones. It may be up to kilo, but I mean, I've been teaching chemistries since 2017, and there hasn't really been many questions on megaliters or gigadegrees. So you don't really need to worry about those. But I mean, since we're all younger and we know about computers more than our parents did, those should be, we should have heard those before, terabyte, gigabyte, megabyte, things like that. But let's start from the base unit. We'll talk about meters, right? So you have a meter, then you have a decimeter. So a decimeter is 1/10 of a meter. So decimal, decimeter. So each decimal place represents 1/10. So 1/10 of the one before. So same prefix. And centi, you recognize that from money, from cents. And there's a national coin shortage. Heard about that? It's pretty weird. Yeah, no one heard about it. Probably because of COVID. They stopped producing coins, and there's a national coin shortage. So you're urged to pay with exact change or with card, which I think coins are going to go out with inflation and with just the amount of technology we have. We're to the point where we can just like take our phone and go, I paid. So coins are going to be a thing of the past pretty soon, especially pennies and nickels. Yeah. Anyway. So you have centi. So a centi, the cent is 100th of a dollar. So a centigram, or a centimeter, is 100th of that base unit. Then you have milli, which is not millionth, but thousandth of that unit. So a millimeter is 1,000 millimeters, make up 1 meter. Then you have micro. So micro is a millionth, and this is the Greek letter mu. So those of you who want to join Greek, are they even having Greek Russian? This because of COVID? No, I don't know. That would suck if they don't, because Greek life is important. It's a good thing. Yes, they are. Okay. Yeah, I was in a frat back in the day. Oh shoot, my professor was in a frat. Yeah. Yeah, it's pretty fun. But anyway, so the Greek letter mu is there, and that means 1/millionth of the unit. Then you have nano, which means 1/billionth of the unit. So that's the smallest one that we're really going to cover. And in my research, I deal with volumes when we're making experiments and making different conditions. With microliters, I deal with a lot. And in terms of molecular affinity of things, we talk about nanomolar for concentrations. So we're very, very small. It's a billionth of a molar concentration. So we deal with those kind of levels there. And milliliters, of course, when we're making bigger solutions. So yeah, and then going upwards, the only one that's super, super important is kilo. So kilo, if you've ever seen Breaking Bad or any drug-related show, right? Oh, a kilo of Coke, right? That's 1,000 grams of it. So, or if you run track, a 5K, what is that? Let's say, if anybody watches The Office, remember the fun run? You ever watch The Office? So the fun run for The Cure or whatever, and Michael Scott put down a 5K as 5,000 miles. And Pam was like, a 5K is not 5,000 miles. So it's 5,000 meters. So that's what the KM, kilometers. Oh, there is a chat. I'm going to see that. Which one? I'm not telling you. I'm not telling you which round I was in. I don't think NJIT has a chapter of it anyway, so it wouldn't matter. But I'm not going to say anything. Because frats have a negative connotation in college life. Mine was good. We didn't really do much crazy. We were just like the frat that went to the gym and studied. So really interesting there. Okay, so here's just some of those measurements that we just mentioned in sentences. Great. Here's an important point. For any of you who want to go into healthcare related fields, like nursing or become a doctor, the cubic centimeter or the milliliter, they're the same thing, also known as the cc. So, nurse, give me 15 cc's of this drug, stat. So that means literally 15 milliliters, nothing complicated. So a cc is a cubic centimeter, is a milliliter. Okay, so I heard your lab is going to be weird, right? So some of you in lab, some of you not. Yeah. Some of you online probably are. Now the lab, I think it's going to be the same as Converge, where some of you are there, some of you are not there. I'm totally against that. I think that's so weird. For lecture, we could do it, but for lab, that's going to be terrible. Like I don't know. Like you have half the students on a simulation lab, and then half of you are trying to, since it's going to be 6 or 7 of you at a time, what, 2 groups, and you can't even get near each other, and the TAs can't get near you, or whatever. Like, how do you? I don't know. But regardless, that's not my problem. That's your problem. Here are some laboratory instruments that you will see. The graduate cylinder. The graduate cylinder. You can see it has tick marks, and each one of these, this is in milliliters. This is the volumetric pipette. I don't think you'll see this until you get to instrumental analysis, which maybe you, the biology major, will get to. But engineers, I'm not sure if you need to take that. So the volumetric pipette, similarly to the volumetric flask, they are volumetric and they only measure one volume. To me, that's dumb. I don't know. They're very, very, very precise, but not just very precise, very, very, very precise. But we use these, and it can only measure, it has one line, and if you hit that line, in this case, it's 25 milliliters. This line is 250. So they only measure that volume. Kind of dumb, but they do that. And then this is a burette. So we will talk about a burette in the next slide, or next couple slides. We'll talk about a burette now. No, we'll talk about it later. We'll talk about it later. Okay, so here they are. Now, mass and weight. So I mentioned that word, the slug. So before I get into the slug, we'll go over the difference between mass and weight. So mass, like I said, is the measure of really, this definition is a little bit different, but it's the measure of resistance of an object to its state, to change in its state of motion. In other words, it's the resistance of it to momentum. Since momentum is mv, that's the equation. So in essence, it's the amount of stuff in it, the amount of physical matter that is enclosed in the object. The weight, on the other hand, is the force exerted by gravity on that object. So there's a conversion. There is 2.20 pounds equals 1 kilogram. I don't like that conversion at all, because it's only true most places on Earth, not even all of Earth. You can go into deep sea trenches, gravity's a little different. You can go into the Appalachians or like DePaolo or something, and gravity's a little bit different because you're further away. So this comparison from pounds to kilograms is technically not a good conversion factor. It's just true on Earth, because if you go to the moon, your mass will stay the same. The amount of atoms inside of you won't change, but your weight will drastically decrease. So if you ever want to lose weight, just go to the moon, and you won't lose any atoms. But yeah, so that's the difference. Okay, so any questions so far? I'll take questions. We've kind of been just bopping around. Online, no questions?
So there is a lab for this class?
Yes, but all of you might not be enrolled in it. So do all of you have to take it or not? I don't think so, right? Yes? You have to take it. Your biology. Are you?
Yeah, I'm biology.
Okay, so you guys have to take it, but I don't think the regular engineering students need to take it. But it does exist, is what I'm saying.
You have to check on like when you register, there's Degree Works, I think it's called, and it shows if you have to take it or not. If you take this as an elective for like a computer science or an engineering, you don't have to take the lab.
Cool. Yeah, that sounds right. Yeah, so I mean, if you're confused, you can go to that, or NJIT does have like a requirement, like a course listing for each major, right? I assume they have that. Every school has that. So you can just take a look at that. Yeah.
I just have a question. So this is chemistry. What is this chemistry principles or principles of chemistry?
Fundamentals of chemistry.
Is there like a big difference between like regular and this?
Between the 121 or 125?
Yeah.
So, no.
Okay.
Yeah, there isn't really. I would say they take this information to more of an extent. So the crazier problems they would get, but the information's the same. So something that me and the other professors were talking about is there's going to be some students that jump from this class to Chem 2, to regular Chem 2, which is the 126. And that is totally possible. You could do that. So the information is going to overlap, or it'll be a great introduction to the heavier stuff in Chem 2, either on 122 or 126. So you can jump either way.
Okay, thank you.
Yep. Okay, so I'm going to get rid of this chat. Okay, so for doing measurements. Now, for measuring something, what time is it? 7? Okay. So we'll take a break. We're going to take a 5-minute break around 7:15 after we go over measurements before sig fig, or after sig figs, we'll take a break. Okay, so for measurements, whenever you're taking a measurement with an instrument, you have a degree of certainty, and then everything after that is uncertain. So you have a certain digit and an uncertain digit, or digits. Really, it's just one digit for uncertain. And while reporting any measurement, you need to have both. So here's the best way I like to explain it. If you measure a meter stick, let's say for simplicity, it only goes by 1 meter. So 1, 2, 3, 4, 5 meters. Fine. And your object that you're measuring is between 1 meter and 2 meters. Your certain digit, you definitely know it's at least 1 meter. But you have an uncertain or estimated digit that you can guess that is in between the tick marks, even if there are no tick marks to guess. So if you think it's more in between, more closer to 1, you can say it's 1.2 meters. If you think it's closer to 2, you could say it's 1.8 meters. That 0.2 or 0.8, that is the uncertain digit. So another way I like to say it is you can guess your estimate one place beyond the most precise tick mark. So if your tick marks are in the tenths, your actual measurement should be in the hundredths. So you can kind of guess that extra digit. All right, so I will show you what I mean. All right, so here's one of these burettes. So here's a burette. So this burette, I guess I'll just point. So instead of just pointing like that, I guess I'll point like this. But you guys can't see it. Oh no. And whatever. So whatever. Burette. So in this burette, you notice something, that it measures volume in the opposite direction that you normally would. You fill up a graduated cylinder, it goes 0, 10, 20, 30, 40, right? In this case, it goes the opposite way. Before I tell you the answer, does anybody want to take a guess why?
So dumping the fluid goes the opposite way.
Say that a little bit louder. I think you're right. I heard dumping fluid. That has something to do with it.
I believe he said because the fluid goes the opposite way.
Yes, yes, it comes out from the bottom. That has a lot to do with it. So close enough. So the burettes, which you'll see in lab if you take it, they're used for mostly these experiments called titrations. And in a simple titration, let's say, well, what a titration is you are determining the concentration of an unknown source of substance, knowing the concentration of a known substance. So what you would normally do is for an acid-base titration, which is the most simple one. Let's say you have a vat of acid or a beaker of acid, and you just know it's 200 milliliters, and you don't know the concentration of it, and you want to figure it out. What you would do is you would put a known concentration of base in here, let's say NaOH, and let's say it's 2 molar NaOH. What you do is you would turn this knob. You turn off your microphone if. Oh, Eric. Good job, Eric. Good job, Eric. Whoever's talking, can you please mute? I can't see. Okay. All right. Anyway, so Eric, good job. So what you do is, for the unknown acid, you put a drop of indicator solution in there. And what that indicator solution does is when enough base is dropped into the acid to neutralize it completely, it changes color. So once it's neutralized, you can go backwards and calculate, all right, if it took X amount of liquid to neutralize it, what's the concentration of it? That's where the burette comes in. It makes our measurements easier. Instead of having to subtract 25 from whatever number it's at, what we do is, this measurement is the amount of liquid that has been added to our unknown solution. So it represents not the amount of liquid inside the burette, but the amount of liquid that was removed from the burette. So you always fill up a burette all the way to 0, and then start removing liquid. And then once you get to your point where it changes color, stop. And then you read it. And that amount, 20.1 between 1 and 2, that is how much liquid was removed from it. So yeah, make sense? Cool. Now let's get to the actual measurement. So this measurement is 20.15, if I had to guess. So why did I pick that? What's the method behind that? So keeping in mind the certain digits and the uncertain digits, here's how you do it. So you first want to read what you know 100% for sure. You know that it's at least 20, it's at least 21, and it's somewhere between 21 and 20, oh, sorry, not 21. Sorry, 20.1. It's definitely 20.1. It's between 20.1 and 20.2. The 20.1 right here, that is your measured numbers, your certain digits. And then what you can do is guess 1 digit beyond the tick marks. So guess 1 digit more precise than the tick marks allow you to. That's where the 0.5 comes in, 0.05 comes in. So your uncertain digit will be just the 5 at the end. So you have that one level of guessing after your real measurement. That make sense? Good, good, awesome. Oh, I turned it off. Also, online people can, after the class is over, if you give me feedback of what I can change to make it better for you. I guess you guys too. But I think this is pretty normal for us. But for people online, if there's things that I can do better to make it easier for you to see, higher quality, whatever, I'm gonna try to get my phone camera to work instead of the owl thing for next class. So I'm gonna try to get 1080p up here, at least. Okay, so I gotta re-click on it. Okay, cool. All right, so this level of certainty and uncertainty, we measure significant figures because of this. So significant figures are the numbers that it includes the certain numbers and the uncertain numbers, or the measured digits and the estimated digits. And it's what makes up our measured number, or our measurement, is significant figures. There are numbers that are not significant figures that don't make up our measurement, that are used as maybe placeholders, or really that's it, just placeholders. But we'll learn about the rules of significant figures after we talk about the accuracy and precision of measurements. So yeah, so first we'll talk about this. Yeah, okay. So I'll cut to the chase. We have two measurements here. We have 25, just 25, and then we have 25.00. So I think for online people, my cursor is probably going all over the place. There's 25.00 and 25. So so anyone want to answer, what is the difference between those measurements in terms of the sensitivity of them, the precision?
25.00 is much more precise.
Yes. So I assume that's what you were going to say. Yeah. Okay. So good. 25.0 is much more precise. And that tells you that the instrument that it was measured with can go to the 10th place, not the 100th place. It can go accurately as a measured number to the 10th place. And then after that, you have one more uncertain digit to give you 25.00 as your measurement. Whereas 25, that's not very accurate. Why? Because this 25 assumes that your graduated cylinder, let's use the pen now. See if this works. We have to turn this off. Oh no. Oh, there you go. Wait. I can do this. Oh, it's up there. Okay, good. Wait, not good. Oh, yes, you can all see it. All right. So it's not here. Oh, it's weird. Okay, so this assumes the 25 that your graduated cylinder goes between 30. Oh, this is terrible. 30 and 20, right? Because the only measured number that you can measure accurately is the tens place. And then the one after that is your uncertain digit, which is the 5. So that's what kind of graduated cylinder you're using for 25. A very precise one that goes to the 10th place is what you're using for 25.00. So it's a very big difference. Okay, so yeah, we got it, cool. Okay, so accuracy and precision. So accuracy is the closeness that you are to the true value that you seek. So let's say you have a 45-pound plate in the gym, right? That's 22.5 kilograms. Right? No, 20.5 kilograms. I don't know. I should know this. I have 4 actually, but I think it's 20.5. Yeah. So 20.4, I mean. Okay, whatever. Regardless, you have this weight, and it says the weight on it. So you should think it's that weight. If you go to weigh it, and it says keep in mind, it's 22.5, or sorry, 20.5. If you go to weigh it, and it says 25, that's not an accurate measurement, because you know your intended value, what it should be, is 20.5. Now, if you measure it again, and again, and again, and again, and you keep getting 25, where you know it should be 20.5, you have a precise measurement. It has a lot of precision because you keep getting the same result over and over again, or very close to it. That's what precision is. It's the degree of agreement among several measurements of the same quantity. So you keep weighing it, but you keep weighing it wrong. So your instrument, there's something wrong with it, but your technique is pretty good because you keep doing the same thing. But in the case of a scale, it could be not calibrated. That's totally possible. So you can have measurements that are not accurate, but are precise. And you can also have other cases of measurements. which we'll talk about now. So here are 3 cases. The first case on the left with A, it is a measurement that is neither precise nor accurate. So you have crappy technique and you have a crappy instrument. All over the place, garbage. Or if you're shooting this dartboard, you've had 1 too many drinks and you see like 4 dartboards and you're all messed up. Or you just suck at darts. So that's one case. Then you have precise but not accurate. So like I was saying before, if you keep taking that, or let's use darts as an example. You're having an off night, you hurt your arm. So to compensate for it, your arm's kind of like this way. So what's going to happen is you have a good shot, so you're going to keep making that same shot over again, but it's going to be a little bit to the right, and it's going to be off. So in basketball, or if you play basketball, usually you see that happen if you have an off day. Usually all your shots going one way off. I mean, I play baseball, I'm a pitcher, so that happens a lot. I keep missing away to righties when I have an off day. Anyway, so that is precise but not accurate. And in scientific terms, what that can mean is that it could mean that there's a problem with your instrument. So my advisor always likes to joke that the first thing I do when we get bad data is I blame the instrument. So that's not the best thing to do. Always question your own technique first, but sometimes it is the instrument. Have the gold standard. Question? No? Okay. So then there's the gold standard of having a precise and accurate measurement, which are all right in the bullseye and sober and throwing strikes. So good. Okay. Oh, wait, what did I do? Oh, this is the one I was talking about. The same thing, but I'll talk about that later. Okay. All right. So is there any questions anybody has? And there should be one.
What about accurate but not precise?
That's the question. Awesome. See, that is a scientific method. You know how to ask the right questions. All right. So accurate but not precise. What that would mean, or I'll ask you, what does that mean to you? What do you think? Where would the darts be?
Would it be like a couple in the middle and a couple off?
Okay, I'll take that. Yeah. So in other words, what you're trying to get at is the average of the dart position will be your target. That's what it means to be accurate but not precise. So your measurements are all over the place, but they so happen to average out at the intended value. Now there's a reason why that case isn't included on here. Does anybody know that reason? Or anybody can speculate based on science and facts and things, facts and stuff. Anybody know why that's a totally valid example, a totally valid case, but it's not up here? Anybody know why?
Was it too complicated to measure the dartboard and average out the distance from the center?
That's a possibility. That's good enough. But in reality, the reason why is because those measurements are garbage for science. If we get measurements that, let's say I'm intended target for a cancer drug, right? Let's say a target affinity for a cancer drug. Really good affinity is single-digit nanomolar, so that's a concentration. Let's say I take the measurement once, I get 3,000 nanomolar. Let's say I take it again, I get 2 nanomolar. I take it again, I get 2,500. Take it again, I get 1. Those measurements are so far off, but if you measure them, if you average them, they might be somewhere in a reasonable where you're looking for. But the standard deviation of those numbers is so large that that has no significance in science. And that data will not be taken seriously. Because to the reader, or to whoever's looking at the data, that shows you have crappy technique, or maybe your instrument's very old, it's very noisy, the signal's all over the place. Even though your average is a good number, the fit or the standard deviation of that data is terrible. So standard deviation is a very important thing. And in every scientific paper, you have to include the standard deviation of a set of measurements in like a side column, just to show that, it's really called the standard deviation percent. to show how far your measurements are off from each other. So if you have like 4,000 and then 4,100, that's not too far off. Even though they're 100 off, the percent of that is like 2%. So that's considered a really good measurement, a really good bound. So yeah, so that's a very good point. Okay, so there's two types of error. Going into error in instruments and science, there's two types of error. The first is random error. And I will draw random error for you. So if you've ever seen any kind of scan, let's say it's a EKG or ECG, EMG, any kind of scientific scan not having to do with the body, really any kind of radio signal, any really took a force meter in physics in high school and got some data from it, you will see this. You will see this. So the signal might look like this, and then I'm going. So let's say it fits and it's supposed to look like that, but it looks like that. That is random error. Something that is limited by the sensitivity of the instrument, can't be avoided. That's still pretty good data. If I went on my instruments and I showed that to my advisor, he'd be like, solid, because it shows a nice fit and it looks pretty good. I mean, it's not as smooth as it could be, but that's limited by the instrument. It's just random probability, and it has an equal probability of being higher or lower than it should be. So it's just the noise, we call it. Then there is systematic error. So systematic error, in this case, let's say the smooth one is what I'm aiming for, would be this. So this is a systematic error, meaning, whoa, my signal looks great, but it's way higher than it should be. So that means there's definitely a problem with my technique. Maybe I added too much volume. Maybe I did something wrong. Maybe my conditions were wrong. Maybe there's something wrong with the instrument, or doesn't have a right setting. Or if we're talking about something as simple as a meter stick, maybe you need to get glasses. But regardless, that is a systematic error, and they can be changed. They can be fixed. So if you have big random error, that's not good. Because if, let's say you get your data, let's say it's supposed to look like this, you get your data to look like this. Qualitatively, it's like, yeah, it's kind of similar, right? But that is way too much random error for you to change. And what that means is you're at the limitation of your instrument. So you can't get more sensitive to that than that. You have to spend money and get a new instrument. So save up that money that I'm not making you buy textbooks with. Okay, any questions on those errors, systematic and random? I feel like I am teaching the lab, how much I'm talking about research and labs. Okay, so back to the dartboards. The one that was not precise or accurate had large random error, not good. The one that was precise but not accurate had low random error but a high systematic error. That's better because you can manipulate something, change something to make that normal again, make that have no error as the third case, which has small random errors and really no systematic errors. So yeah. Okay, so we know this is easy, I don't care. Okay, all right, let's do this one. So we have a burette up here. And can anyone tell me what you would report the volume of the burette? You might have to look at it closely. It's very pixelated. So what would be based on what we learned about measurements today, what would be the correct measurement?
22.
22. I don't know.
22.0.
Oh, 22.0. I like that better.
0?
No, not that one.
Oh.
The second answer. Who was that? Who was the second answer?
Me, Alex.
Alex. Great job, Alex. Yeah, I'm sorry, because with this setup, if you might have to say your name because I can't really see who's talking as you're talking. I can figure something out for that, but okay, good job, Alex. We'll just go with the flow. So Alex said 22.0, and the reason why is because you look at here. All right, it's definitely 20. definitely 21, and it's very even with 22. So that means I know it's 22 is my measured number. Then my uncertain digit is one beyond that, one beyond 22. So I think, so that could be estimate, that could be guessed. But looking at it closely, it seems to be right on the line. So I'm going to put that as 22.0. No reason not to. If it was in the middle, right here, it would be 22.5. But 22.0 is the right answer. Good. Okay. Okay, so I guess we'll do this one. So here's 3 trials of measuring boiling point, 22, 22.1, 21.9, but the actual boiling point is 28.7. So can someone tell me what is, in terms of precision and accuracy, what is this measurement?
It's precise but not accurate.
Good. They are precise and not accurate. They are around each other, but they are very far off in percentage-wise from the actual number. It's probably like 25 to 40, maybe 40% off, not 30% off. All right, we're good. Whatever, we did that. We know this already. Okay, so the rules of sig figs, and then we'll take a short break. So sig figs, significant figures. I hate sig figs, but you have to learn them, and they're gonna be a pain in your ass. But there are non-zero numbers in measurements. Every time you see a non-zero number, it is significant. Why? Because you measure it. If you measure it, it has to be part of the calculation, right? Or part of the measurement. So you see those and you record them. Then there are zeros. Zeros are kind of tough because there are 3, actually technically 4 classes of zeros. The first one is the leading zero. So the leading zero really acts as a placeholder. Oh, I like what I just did here. I have the gyroscope synced up with my hand. I'm using it and controlling it with my left hand. Looks like magic. All right, so the leading zeros, they act as placeholders here. So this number can be that can be condensed down to a scientific notation, which is the preferred way of doing it. So that leading zeros are not significant figures. Then you have captive zeros, or otherwise known as sandwich zeros. So sandwich zeros are always significant, because how can you measure this 4 at the ones place without measuring all these zeros in the middle? That means your instrument has these levels of precision to get to the 4, to get to the lowest level, or to get to the highest level of precision. Then you have trailing zeros on the bottom. Here's my gyroscope. Whatever. So you have trailing zeros. So trailing zeros, there's 2 cases. The first case, where you have no decimal point. So you see that big number, 3, 4, 5, and a lot of zeros? You have no decimal point there. In that case, those zeros are very similar to the leading zeros. They just act as placeholders. And I'll explain more of that when we do examples. With the decimal point, as the second example shows, with 3.45 and a bunch of zeros, those zeros at the end, they are significant. Just like when we compared the 25 to the 25.00, that 0.00 is significant because it tells you that measurement can go that many places more precise while still being a reliable measurement. The instrument can go that far. So when you have a decimal and trailing zeros, they're significant. I mean, if you just memorize those rules, you should be pretty good, but we're going to do examples of those now. Exact numbers, okay, what's exact numbers? What an exact number is? So, okay, sig figs only count for measured numbers, things that you measure, measurements. Exact numbers are another type of number that are either by counting or by definitions, by conversion factors, things that are set in stone. So I can't say there is 1, 2, 3, 4, 5, 0.00 students in this room. I can't say that. There's 5 students in this room. That's an exact number. It's counted. Integers. So let's go back to sig figs. We talked about these zeros already. Now trailing zeros. So trailing zeros are only significant if the number contains a decimal point. And that's, like I just said, for more level of precision. If it doesn't contain a decimal point, such as 300. Oh, it looks like the font of the movie 300. It's in red, like that. It's got the little wick thing. That's cool. Anyway, so 300. This number tells me that our beaker is actually like this. So here's 0. Here's 1,000. Oh, yeah, that's 1,000. Okay, ignore that line. So that's what this beaker tells me. That's what this measurement tells me of 300 with no decimal. It tells me that the beaker goes from 0 to 1,000, and my liquid is somewhere there. That I'm going to make that, the only thing I can do is make this is an estimated digit, an uncertain digit of 3. So I'm going, all right, 300, about 300. The other numbers are not significant. So putting this into a scientific notation, it would be 3 times 10 to the 2. And it would only have one significant figure, only the 3, not the zeros. Make sense? Okay. Best way to learn this is by examples. So the first example before we take a break is this one. The 0.0105. So how many sig figs are in that number for A? 5. No. 3. Yes, good. Okay, both of you guys, good job. So it was either 5 or 3, right? So it is 3 because even though there's a decimal point, these are leading zeros. So that's where this stuff gets confusing, because you would think, oh, the professor said, okay, decimal point, significant, right? But it's only the trailing zeros that are significant when there is the decimal point. So these are leading zeros. If there's a decimal point or not, they're not significant. So they would only be 3. Okay. More complicated number. What about this one? Letter B. 0.050080.
5.
Correct. Good. There's 5. Awesome. And there's 5 because, like I said, the leading zeros don't count, and the 5 counts, the 2 zeros in the middle, and the trailing 0 counts because there is a decimal point. So yeah. What about this one? 8 for C, 8.050.
4.
Good, 4, because everything counts. You have a decimal point, and the trailing 0 counts. Okay, so is there any questions on that? So let's continue the class. So everyone should be back online. If you went to get dinner or something, let's go back here. So I'll make a note, 7:36. That's when I'm going to cut the video to start again. Okay, so with significant figures, now that we understand which numbers are significant, we are going to talk about doing operations with them, because this is the most important thing. When we're not just going to be taking measurements, we're going to be adding, subtracting, multiplying, and dividing these measurements by each other. So we'll go through this kind of quickly. So for multiplication and division, what you're going to do is you're going to take the numbers that are the least precise in terms of the number of sig figs, the least sensitive. By sensitivity, I mean it goes to something that's a very sensitive number, it goes to the most decimal places. Because I don't like using the words precise and accurate for that, because we just learned that there's something different. So I mean sensitive. So we take the least sensitive number, and that is the number of sig figs that we're going to use for the answer. So if you put in 4.56 into the or times 1.4 into the calculator, you would get 6.38. But we know that our least sensitive number is 1.4. So that means it has 2 sig figs. Our answer should have 2 as well. Make sense? Cool. For addition and subtraction, here we go. I can do the wheel. Oh, it's off. That explains a lot. There we go. So for addition and subtraction, it's the same concept where you want to do as many numbers as your weakest link, but it's not total sig figs. It only corresponds to the number of decimal places. So you're taking your least sensitive number and you're going to that many decimal places. So you're going, so this one has 2 decimal places, 1, 3. So that means your answer in the calculator will be 31.123, but your least number has only a tenths place, so your answer has to be just to the tenths place. Any questions about that?
Would rounding up bring that to a 2 if it's over 5?
Yes, yes. So if this was, good question. So if this was 31.15, this would be 31.2 would be your new answer, because you're basically rounding to the number of decimal places that you have to based on whatever numbers you're adding or subtracting. Same with multiplication and division. So you're rounding to it. Okay. Yeah, so this is basically, that's what it's saying next, to round. Okay, so let's do these examples. Oh, question? No? Okay, so let's do these examples. So can anyone give me the answer for A? And online people, you should know it because it's kind of there. Anybody?
0.171.
So the answer is 0.1, and since online people can see it, we'll just go. Okay, so the first one is 0.071 because 0.171. Yeah. So the least sensitive number is the 1.05, which has 3 sig figs, and the most sensitive number is 4, so you go by the least, 0.171. For the second one, your answer would be 7.2. But our least sensitive number only has the ones place as its most specific or most sensitive digit. So you have to go to the ones place, rounding from 7.2 down to 7, or no decimal places. Make sense? Cool. Now I'm going to give one example here that's tricky. 30 plus 1. What's 30 plus 1? 31. Well, yeah, but in sig figs, what is it?
30.
30.
30, good. So it would be 31, but you have to round down to 30 because your least sensitive digit is the tens place. So that's another thing you have to keep in mind. They try to throw curveballs like that to you on the homework. If this was a 5, what would the answer be?
40.
Good, 40, because the 35 rounds up to 40, which is to your tens place, like that. Cool. Okay, any questions? No? Okay. All right, so for multiple operations, when you want to do addition and subtraction, or addition and multiplication, what you're going to do is you're going to follow PEMDAS, which is parentheses, exponents, multiplication, division, addition, subtraction. Yeah, I know what that means. So you're going to follow PEMDAS, and you're going to use the correct number of sig figs in each step. So the first step would be addition, or really, well, you could do it this way. You don't really have to follow PEMDAS. I mean, you do. There's different ways to break it up. Or you could break it into 9 points, but I would you add the top and then divide by the bottom. That's how you're going to do it in this case. So you're going to add the top, and then you're going to get a number with 1 decimal place, because your least sensitive number, these 3, have 1 decimal place. And then you're going to divide that number by 4, and your answer will have 1 decimal, or 1 sig fig, because the 4 is only 1 sig fig. And I don't know what the answer is. Should have wrote that. But yeah, so does that make sense? You're just going to follow the order of operations, but you're going to use sig figs in mind. Keep sig figs in mind for each step. Okay, so express this in scientific notation quickly. Which one? Anybody?
C.
A.
A. So it's not C actually, tricky, because sig figs. So this number, 3,140, has only 3 sig figs because there's no decimal. So our scientific notation version of it also has to have 3 sig figs. So 3.14 times 10 to the third. Okay, there's another one. We can skip this one. We can skip this one too. All right, so now we're going to go into probably the hardest part of chapter 1. I feel like I was talking way too long for the first one, but I do want to focus on this. So it's a unit conversion, dimensional analysis. So for this, I'm going to sit down, and I'm going to sit down. But what I'm going to do is I'm going to be able to write notes on the slides. So this will probably, if I go out of here, I will duplicate. What's it doing? Did it freeze? No. Did it freeze? All right, I guess we're gonna keep going this way. I have an i7, man. 8th gen i7. Shouldn't do that. What do you got in that Alienware?
HN I9.
Okay. We can switch. Oh, you want to keep your ink annotations. Oh, that's why it froze. You can ask me that. And I don't want to keep them. Can you click it? How do I get there? Oh, there we go. Nice. Okay, cool. All right. So now I can sit down. Okay, so we're going to learn by example. So the first example we're going to do is this one. So you want to order a bicycle with a 25.5-inch frame, but the sizes are only given in centimeters. What should you order? Basically, it's asking you to convert from inches to centimeters. Now, for general tips for any unit conversion problem is write down, so I'll write tips. Not right. So write down conversion factors. So for every measurement, you're going to be using one or more, or every conversion, you're going to be using one or more conversion factors. In this case, it's a very simple one, going from inches to centimeters. And we happen to have a conversion for that. And also, they will be given. So there's no need to memorize these ones. The only conversions that you do need to know by heart are the SI unit scalars, so the prefixes, kilo, deci, centi, all those. So for centimeters to inches, we have 2.54 centimeters equals 1 inch. So after that, what we're going to do is we're going to write down our measured number. So that's write measured number. Then manipulate. Okay, so all these processes should flow very smoothly. So here's what I'll do. You first write down the measured number. So in this case, we have a 25.5-inch frame of a bike. So 25.5 inches. So then we're going to take the conversion factors that we have that involve inches, and we're going to multiply or divide to get rid of inches and move it into our next unit, which is centimeters, which is our final unit. So inches times, and the way to do that is you multiply it by the equality. So the equality is 2.54 centimeters over 1 inch, or vice versa, or 1 inch over 2.54 centimeters. So based on math, on algebra, which one would you put on the top? The centimeters or the inches? Good, the centimeters. Because you want centimeters to be your final unit. So the final unit on the top. Final unit equals top. Then on the bottom, you'll put 1 inch. And then you will cancel out. So you see how the inches in the numerator cancel with inches in the denominator, and you multiply 25.5 times 2.45 or 2.54, 25.5 times 2.54, and you get a syntax error because I put the wrong thing in.
64.77.
Great. Okay, you could teach the lecture for me. Yeah, 64.77. But that's, well, technically it's not the right answer. You fail. But because of sig figs. So based on sig figs, what's the right answer?
64.8.
Yeah, 64.8. Awesome. So 64.8 is the correct answer because our measured number here, the 25.5, has 3 sig figs. So that is the least sensitive number that we're dealing with, since it's the only one, and we use that as our sig fig number. And the reason why we don't use the 1 in the inches is because this is an equality. So the 25.54 equals 1 inch is an equality. And equalities, by definition, are a definition. And they don't have sig figs at all. It's not 2.4500, it's just 2.45. Okay, so does that make sense? That's an easy one, but we're gonna do harder ones now. All right, I hate how this is why I always do the scale down slideshows. They write down how to think. You have to tell someone how to think. You can't just write it down. But these are good questions, I guess. Where are we going? How do we get there? Kind of thing. That's what you need to be thinking. Oh, did I give the wrong conversion? Wait a minute. Did I put 5.4? Yeah, I got that right.
You wrote 5.4, but you said 4.5.
Oh, I did. Oh, okay. Oh,
You were right.
of course. I had an 8 a.m. class this morning, so or I taught an 8 a.m. class.
You're good.
Right. So let's do another one. So miles and kilometers. So a student has entered a 10K run. How long is their run in miles? So first, we're going to write down the equalities. So we have 1,610 meters equals 1 mile. What if I just gave you that? You could still solve this, right? So we're going to write, I just give you this equality. And now we are going to write down the measured number, which is 10.0 kilometers. What do we do now? Anybody?
Wouldn't you rewrite the equality to have the mile on top because you want the finished one to be on top?
Totally. That's a good first step to do. So you want the mile to be on top because that is your final unit. The final unit should be in the numerator. Now what? You still can't use it directly.
You would have to multiply the entire equality by a certain number. I can't think of it.
You have to
But like,
Oh yeah, one of
What are you unit conversion? A unit conversion?
yes. So unit convert. So okay, the reason why that I think everyone knows how to do it. It's either you can't say it or you're thinking of multiple reasons, multiple things. So there's actually several ways to think about doing this. You could do this. You could do this. You can convert 10K, 10 kilometers to meters, 10,000 meters, and then you can use the equality directly. You can convert the equality to 1.61 kilometers per mile, and then use the equality directly. And that's the only 2 ways. Yeah, so that's the only 2 ways you can do it. But you can do it multiple ways. So these unit conversions is my point, that these unit conversions, even though I teach it, I'm doing this, this, and this. There are several ways to do more complicated ones. So if your mind works a little bit differently, I like to think really simple. For those of you who are really good at math and really intuitive with calculations, you have your own way of doing it from high school or from other classes, go for it. I'm not gonna grade you on how you're writing it out. I'm just gonna grade you on your answer and if it's correct or not. So if you have a way of doing it, do it the way your mind works. I can't teach you to learn differently. I can teach you what to learn, I can't teach you how to learn. I like that quote. That's a good quote. I'm gonna put that on my NJIT bio on the website. That quote. I can teach you what to learn, but I can't teach you how to learn. All right, so what I'm gonna do here is I'm gonna put the 1 mile on the top, and I'm gonna put 1.610 kilometers on the bottom. And then I'm going to cancel out the kilometers. 10 divided by 1.6. Yeah, you get this. You get 6.21 miles. So yeah. Okay, any questions on that? I'll give you a second. No? Okay. All right, I like this one. So now we're gonna get a little bit more complicated. And in this case, there's more than 2 ways to do it. So a Japanese car is advertised as having a mileage of 15 kilometers per liter. Now, who's ever heard of gas mileage in that weird unit? We're used to MPG, miles per gallon. So we're given 2 conversions in this case. We're given the kilometer to mile, which we've seen, and we're given the gallon to liter. And I noticed, like, so funny things, like going to the gym and like living like a bro, whatever lifestyle, it teaches you conversions because like you have conversions on the weights and you have conversion on your gallon jug of water. So that's where I actually learned the gallon to liter one, because I looked at it, oh, 1 gallon says 3.78 liters. So that's how it's stuck in my head. So you see these things every day, no matter what you do in life. Okay, so what we're gonna do first is write down the measured number. But in this case, the measured number has 2 components. It has the 15 kilometers divided by 1 liter. Not just divided by liter, it's per 1 liter. That's important. So it's a very full question to ask, what do I do first? Or how do I convert liters or kilometers per liter to miles per gallon? So can someone take me through what your mind thinks? So just, what would you do? You don't tell me exactly what numbers, but what would you do?
Change the kilometers to miles.
A good start. And then what would you do?
Then convert the liters into gallons.
Yeah, that's pretty good. And there's one more thing at the end. What would you do at the end?
Find your value at 1 gallon.
Good. In other words, divide them. So awesome, great job. So what's your name?
Jonathan.
Jonathan. All right, nice job, Jonathan. All right, so that's the exact way that I like to approach these problems. I like to take them 1 number at a time, convert that number, and then convert the next number, and then manipulate those numbers after they're converted. There are ways to do different ratios and kind of like do it in 1 step. That gets too complicated for me. Think very simply, and you'll get it right every time. So the first thing I would do is convert the kilometers into miles. So 15 kilometers times 1 mile over 1.61 kilometers. Kilometers will cancel out, and you get 15 divided by 1.6 gives you a number. Well, it does give you.
24.
I got 9.31, 9.32, or 9. In sig figs, it would be 9.3. That'd be 9.3 miles. Not looking good if it's 9.3 miles per gallon, but we didn't do the gallons yet. So liters, 1 liter converted to gallons. We're taking the 1 gallon and putting it on the top, and 3.78 liters and putting it on the bottom. The liters will cancel out, and you get 1 divided by 3.78, which is 0.26.
She said all right. Did you hear her? She said all right.
So in sig figs, this would actually be 0.3 because the 1 liter is our measured number and it only has 1 sig fig. Okay, so I know I went through that kind of fast. Is there any questions up until this point? So I basically just did 2 unit conversions separately. The 15 and then the 1. No? Okay, cool. So now we're going to do our final step of dividing the 2. So we're going to divide our miles, our 9.3, by our gallons, our 0.3. So 9.3 divided by 0.3 equals 31. That's pretty good, solid. 31 mpg. Okay. Cool. So is there any questions on that? I'll let you guys write it out. Take a couple minutes or a couple seconds. No? Pretty good. Cool. All right. So let's see what the notes come up with as the answer. I got 31. Did they write the answer? I guess not. All right, whatever. All right. So good. All right. So any questions about dimensional analysis or unit conversion up until this point? No? Oh, so another thing I'm going to do is on Canvas, there's a worksheet of dimensional analysis problems, I think. It might be for the 125 class, but even if it is, I'll put it up for your class too. And what I'm going to do is I'm going to make a video of me going through it and solving harder ones and putting it up just so you guys have more content. All right, so the next thing we're going to cover is temperature. Now I will stand up again for this. The owl thing, you can follow me. That's why they call it owl. It's like on a swivel. All right, so there are 3 units of measuring temperature. There are obviously Fahrenheit, which we know and love, and then there is Celsius, and the new one, which is Kelvin, which is the SI units. Now, for Fahrenheit, I guess we'll just cut to the chase. Here's the scales for all of them. Now, Celsius and Fahrenheit are very similar. No, Celsius and Kelvin are very similar. Fahrenheit is the oddball, just like every other American unit, right? So the difference in, I guess normally I would say the difference between boiling point and freezing point of water, but they say that the difference between freezing point and body temperature. Sure, it gets the same point across. The difference between freezing point of water, which we know is 32, and the average body temperature, which is 98.6. I want to know something? Actually, it's lower. So they've been doing that number is from like the 40s, and they just kept it through. But humans have been, I don't want to say like micro evolving, but like very slowly over time, that the average temperature is actually lower than that. It's in the 97s. And just to test that, I took mine today, even though I'm an individual. I took mine today, mine was 95.5. So like, I'm so cool, right? So Alex is back. Cool. All right. So, the difference between those 2 temperatures is 66.6. Okay. The same difference in Celsius is only 37. It's between the freezing point of water and the body temperature. And the difference in Kelvin is, well, the difference is 37 also. The difference is 37, but the number is 310. So what that makes sense? Okay, so what I'm trying to say is the temperature value of the unit for Celsius and Kelvin are the same. If you look at the conversion, so here's the conversion from the 37 Celsius from here to Kelvin. All we did is add a number. We added 273.15 to get to your Kelvin temperature. Whereas the Fahrenheit to Celsius conversion is a lot more complicated. What that is you're taking your Fahrenheit number, you are dividing it by 5 degrees Celsius per 9 degrees Fahrenheit, because that is the ratio of the units. So 5 degrees Celsius is equal to 9 degrees Fahrenheit. So each Celsius degree is more heat than each Fahrenheit degree, in essence. So that's why, like, water goes from 32 to 212, that's when it boils. For Celsius, it's 0 to 100. So it's a lot smaller scale. So each number counts for more. And then for Kelvin, you're just adding on to Celsius. So now the big question is, okay, what the hell is Kelvin? Why is it important if we just got it from Celsius? Why do it? Now, this guy, his name happened to be Kelvin. No, it was Kelvin, and he invented Kelvin. He was like, all right, there's got to be a limit to how cold something could be. And he was right, there was. So that's around the same time they were doing a lot of thermodynamics. And they figured out that cold isn't really a thing. So what cold is the absence of heat. There is a limit to where you can take out all of the heat from an object, from particles. This is on the atomic scale, so very micro, singular atoms and even neutrons. You can take out the movement or the heat. So heat is, we'll learn about this when we get to thermodynamics, but heat is a measure of molecular motion. The molecular motion causes heat. If you take away the molecular motion, you take away the heat and the thermal energy. So Kelvin was like, there's got to be a limit. And he did some calculations, he found the limit. The limit was negative 273.15 Celsius. So Mr. Kelvin was like, this is weird, that's a random number. So I'm going to make a new scale based on that number. And I'm going to say, that is my starting point at negative 273.15 so that there's no negative numbers. There we go. So I'll say that. And then he went ahead and he called it the Kelvin scale. This is the absolute temperature scale. So 273 Kelvin is freezing cold. That's 0 degrees Celsius. So that's like pretty cold for outside. Now I'm going to give you some temperature comparisons, this is cool. So boiling point is 373. So that's pretty hot. That's really too hot for us. We would die. So now let's go to how cold the environment and things around us can get. So we'll go from 32 Fahrenheit, which is kind of freezing. We need a jacket. That's going to be 273. That's 273. Now the coldest temperature on Earth ever, which was actually not the Arctic. It was actually somewhere in Russia, like the Russian tundra. It's like super cold up there. Crazy, crazy stuff. It was negative 120 Fahrenheit, I think, was the coldest ever. So for that, like you need like a warm air mask that like brings in, like you can't breathe the actual air. Like it would like frostbite your lungs and like your esophagus. So it was extremely dangerous. I'm sure there'll be that one kid going to class wearing flip-flops, even in that. So that's a college meme that I love. You'll see when snow starts coming, there's gonna be that one kid who wears shorts and flip-flops to class. It's always that kid. And if you are that kid, I'm sorry. So what was I getting at? Oh yeah, so that's on Earth. So that degrees, so negative 120 Celsius is equivalent to like, I don't know, rough estimate, 180 Kelvin, right? So around like 180. So that's too cold and we would die in like 20 minutes from like frostbite all over. Like our organs would shut down from breathing that in. Then you get to, let's go out of Earth. Let's get to the high orbit or like out of space area. Even around Earth where the sun's coming down, but it's still really cold. And that's gonna be around 10 Kelvin. So you're going to go from 180 Kelvin down is the coldest on Earth down to 10 Kelvin. That's mind-blowingly cold. And you're like, wait, how come there were astronauts up there? Well, that's why they wear the suit. So it's not because of radiation's a big thing also, but if you're exposed, if you're outside of Earth's magnetic field and ozone and out of the atmosphere, and you're just exposed to solar radiation, you won't die. It'll increase your chance of getting cancer, but you're not going to die from it. What you will die from is the cold. So that's why these astronaut suits, they have that heat insulating, that silver heat insulating aluminum material, whatever, I don't even know what it is, but that's what the suits are lined with, because to prevent the cold from coming in. So that's around single digit Kelvin out there. Then you want to go further out, you go to Pluto. Pluto is like 1 to 2 degrees Kelvin. So that's like 5-fold less than around the sun, or not around the sun, around the Earth. So super cold, crazy cold. Then you're thinking, all right, what's the coldest ever? So get to the point, professor, it's late. All right, well, the coldest temperature ever recorded or ever seen in the universe has actually been at a lab at MIT. And they did an experiment on a very small level where it was, I think, a couple of protons. And they did something where they, like, I read a paper on it. They something with colliding. They didn't just like dump ice cubes on it. They put did some kind of thing where they bounced the particles off of each other to like cancel out their motion completely or something. I don't know. I could be completely wrong, but they did something on like a very thermodynamically energy level rather than just making it cold. So they got to, okay, that's not working. Okay, they got to 0.670 zeros and a 4 Kelvin. That's insane, right? So the coldest thing has been on Earth. So, well, that's not true. The aliens probably have us beat. They have something, they probably reached, they're like, oh, 0 Kelvin? That was like 1,000 years ago. Come on, get with it, humans. Oh, I see the owl looks like an owl. It's got the 2 eyes in the front. I just noticed that now. Like the thing looks like an owl. It's cute. All right, so we've seen this conversion already. Now the conversion for Fahrenheit to Celsius will be given on the exams. So I'm not going to really cover it too much, but there it is. So you put in the Fahrenheit temperature here, and you get the Celsius temperature spit out. Okay, and you can, the same thing the other way around. If you solve for temperature Fahrenheit, you get temperature Celsius times the ratio of Fahrenheit to Celsius in terms of their unit similarity, and then plus 32. So yeah, those are 2 there. Okay, there it is summed up, but they will be given on exams. Now, fun thing is that -40 degrees is the only temperature on the Celsius and Fahrenheit scale that are the same. And that's just, the equations work out that way. I don't know why. They just, well, I do know why, because mathematically it works. But that's a cool coincidence. Okay, so let's do a question. So I'll bomb out of that. This. So you have a boiling point of liquid nitrogen at 77 degrees Kelvin. What is the temperature in Fahrenheit? All right, so back to unit conversion. So I'll get my pen out. Let's write our conversion factors. So we know, or what we know is that 273.15 plus Celsius equals Kelvin. And also we know that Fahrenheit equals Celsius times 9/5 plus 32. So can someone quickly say, what would we do? How would we solve this?
Subtract 273.15 from 77.
Yes. So good job. What's your name again? Harrison. All right, good job, Harrison. So what you will do is what Harrison said, is we're going to subtract 273.15 from 77 Kelvin. In other words, put the 77 Kelvin into the equation to solve for Celsius. So subtract minus 273.15 minus 273.15, and you get a number in Celsius, and that number is 77 minus 273.15, and you get negative 196.15. Okay, so now what would you do?
You plug it into the equation.
Exactly. So yeah, you plug it into the equation. Good old plug and shove. So you're going to take the Fahrenheit and equals Celsius, which is now negative 196.15 times 9/5 plus 32. and that will give you your answer. And I think the answer is, here we go. So negative 321 Fahrenheit. Okay, so any questions on that? That's kind of like a two-step unit conversion, but you're using the equations to convert. No? Did everybody online fall asleep? Maybe.
No, I mean,
Great. As long as you're here, we're good. All right, so there's more conversions. You can do those on your own. Density. So density is an important property. I will stand up again. Okay, so density. So density is the measure of how much stuff is in an object per amount of object. In other words, the amount of mass or matter it contains per unit of volume. And the way to represent that is simply mass divided by volume. And the units for it could either be any mass unit over any volume unit. So I forgot to talk about the slug. The American unit for weight or for mass is a slug. So you can have it in slugs per gallon. That's a totally valid unit, but that's terrible. Nobody would use that. But most commonly, density is found in gallons, or not, in grams per liter, or milligrams per liter, grams per milliliter. In chemistry is very common. So those are some type of gram over some type of liter is what you'll see. Okay, so question. So a chemist is trying to identify an unknown liquid. Finds that 25.00 centimeters cubed, or milliliters, of a substance has a mass of 19.625 grams at 20 degrees Celsius. What is the density of it first? So we'll figure out the density first. So what would you do for the density? How would you figure it out? I know it seems like a stupid question maybe, but somebody.
Mass over volume.
Exactly. So I just want to make sure you're awake. So 19.625 divided by 25.00. And wait, how many sig figs will the answer have?
2.
Or
Good. The 4s have it. And the reason why is the 25.00. These are trailing zeros with a decimal. That means they're significant. So 4 sig figs, this one has 5. So the answer will have 4. And what is the answer? We'll figure that out right now. So we're going to do 19.625 divided by 25, 0.785. So we're going to look at our chart of our compounds and their density. So density is a trait that is compound specific, meaning each compound has its own density. Not saying that every compound has a different density, but a density is a, what do you call it? Like a characteristic feature of a compound. So there's no such thing as ethanol that doesn't have a density of 0.789. It's just something that ethanol has. There are totally other substances that have the same density, but ethanol has that density. And since our answer was 0.785, isopropyl alcohol seems to take the win, and that seems to be our unknown substance. So that is a very important way. That's a long time ago, back before they had mass spectrometry or other analytical techniques, to figure out the identity of a molecule of a sample is by just finding the density of the sample. And that can tell you not only, well, maybe if it doesn't tell you what it is, it at least can tell you like what type of compound it is. So these are all organic, and organic compounds most of the time have less density than water. Water has 1 gram per milliliter. A lot of alcohols are always less dense. So it can give you an idea of what it is. All right, where are we going? How do we get there? What do we do? All right, we did that right. Yeah. Okay, cool. So here's some densities of some common things. So we have oxygen, hydrogen, he has a bunch of stuff. So the most dense things are going to be metals. The metals are very dense, obviously, right? Does anybody know the most dense metal in the periodic table? No? I think it's tungsten. Tungsten. I'm going to double check that. The professor's on their phone. Most dense element. Oh. Might be osmium. Wait. Let me see. Oh, osmium. Fine. Tungsten second. Whatever. Whatever. Fine. All right. Got me. Got me, Google. Okay. So the last thing we're going to learn, which is extremely easy, is states of matter. So any questions about temperature or density? No? Okay. Oh, there's a chat. Somebody in the chat. Where's my mouse? Here it is. Oh, what's the difference between intrinsic and extrinsic properties? Was that covered here? But anyway, I'll tell you. So an extrinsic property, it depends on the amount of mass. And an intrinsic property, it doesn't. So something like density. Well, I probably said that for density. That's why you asked that. I kind of just went over it. I kind of just like, meaning I ignored it. There you go. Where does it say it? Okay, well, density is an intrinsic property because it doesn't matter how much of the substance you have, the density of it is still the same. If you have a large amount of it or a small amount of it, it's still a characteristic density. The extrinsic property, on the other hand, such as mass very much determined by how much stuff you have. The more of it you have, the mass of it is higher. So, yeah, but that wasn't on here. Anyway, good question. Okay, all right, so matter, there are three states of matter. There is solid, liquid, and gas, which we all know. Now, something I will say that maybe you don't think of it in this way is the way you go from solid to liquid to gas, or go the other way around, go from, yeah, solid to liquid to gas, is by increasing degrees of molecular freedom and increasing energy. So we're going to be learning about this concept, and I kind of already prefaced it with energy and heat corresponds to molecular motion. And this definitely, this shows that the best. Because when you have a solid has a low energy particles. They're moving, they're always moving. Every particle is vibrating, every molecule is vibrating, but they're doing so slowly. And they're not really moving too much, not flowing, definitely, but they're just shaking, right? It's like a crowded dance floor where everyone's just like doing something, right? But they're not really moving around. But then you heat it up. People want to move more. And people are sweating, they want to get out of there, they want to move, right? Molecules do the same thing. They want to increase their degrees of freedom. They move more. And what this does is it shakes up the solid. It moves it around. The molecules move, and eventually they reach a point known as the melting point. And the melting point, it varies per substance, because each substance, the reason why it varies is because each substance has different forces of molecule to molecule, and those forces need to be disrupted in order for it to flow from a solid to a liquid. So water has a pretty high boiling point or melting point because the forces of the hydrogen bonds in between water molecules are very strong, and it requires a lot of energy to melt them, to break them apart. But they're still water molecules at the end of the day. They just flow more. And we'll learn about that more later. But solid to liquid, you have the melting point. Once you add more energy to these already flowing molecules that can move freely, you're going to have more motion, more speed, more thermal energy, to the point at which they are released and they're free as gases, to where they boil. That's the boiling point. And there, the degrees of freedom increase to the maximum level. And then you can ask, what happens if you add more energy and more heat, more movement to gas molecules? The answer is nothing. They just move, well, nothing significant. There's no fourth state here. Well, there's plasma, but that's different. Something, not everything can make a plasma. But what happens is they just move faster. And there's an infinite speed at which gas molecules can move. I guess when they approach the speed of light, that's the limit. But they can really go a lot faster if you just add more energy. So taking this into notes, a solid is going to be rigid. It has a fixed volume and shape. And they're slightly compressible depending on the solid, but not really. You're going to have a lattice, or not lattice, a lattice, meaning a solid, a three-dimensional shape that gives the structure rigidity, and it allows the molecules to really stay stationary and fixed in a solid manner. So really the only thing important is just know what a solid is, and know that it's fixed volume and shape. Then when you increase the molecular motion, when you increase the speed, increase the thermal energy, these are all the same things, by the way. When that happens, to the point of past melting, you have a liquid. In the liquid, you see there's no more lattice. They're not chained together. They're free-flowing. This gives them, they said they have a definite volume still, because they can't go three-dimensionally yet. They can only go, or they can't go, they can't disperse up. They're going to disperse left and right. But they have no specific shape. So you pour water on the floor, it's no longer the shape of the water bottle. Common sense, right? And they're slightly compressible. But the real magic happens when you go to the next level, when you add more thermal energy, more molecular speed, more kinetic energy, and more molecular motion, is you have the gas. The gases are heavily compressible because they are so far apart from each other compared to their sizes that they could be compressed a very large amount. Whereas liquids, so if you saw here like liquids and solids, all the molecules are very close together, even in liquid, but they just flow. Solid, or gas, they are very far apart. So, yeah, very far apart, and they move randomly and they bounce off of each other. Okay, any questions on that? All right, I'll give you one more. So we're almost done actually. So I'll give you one more thing before we leave. Well, then we got to do mixtures, but when we're on gases. So this is going to change the way you think of the world after this, or the environment. Okay. So you have, you breathe out, right? You breathe out gas. You breathe out oxygen gas. There's four or five types of gases in the air. There's mostly nitrogen, there's oxygen, there's argon, there's CO2, very trace amount of CO2, only 0.04%, but it's there. And there's other things, hydrogen gas. But so the average speed of gas, so this picture shows the gases are moving very fast. And that's true because you gave them all that energy to boil out of something, or they have all this energy. They're going to move very fast. The average speed of one of these gas molecules, even in the air that we breathe, the air that we're in today, is 0.5 kilometers per second. So that's 500 meters in a second. That's the average velocity of a singular nitrogen gas or oxygen gas that's in our atmosphere. So you might be thinking, whoa, that's really fast. How come we don't feel it, right? Anybody have any ideas? How come we don't feel it? And the answer is not because they're so small. Because there's so many of them, right? If we had a wall of millions of atoms, or molecules hitting us at that speed, we would go flying. So why is it? If you're too tired, I'll just tell you the answer.
It passed through.
Good thought, but they don't pass through because we're pretty solid. We go to the gym, we're pretty solid. Nothing passes through us. Nothing gets through. But on the right track. So they don't pass through, but it's well, not the right track. It's the opposite of that. They don't get to you. They don't get to you because, anybody know why? Anybody speculate? No? All right, I'll tell you the answer. So they don't get to you because who is telling all the gas molecules to move in the same direction? Nobody is. They're just free, they're bouncing off of the container, which is the room, and they're just going wherever they want. So eventually, there's so many of them, there's billions and billions of them, that they will collide, bounce off each other, collide, bounce off each other, and do that very rapidly. So right now, you are all, at home and in the classroom, in a three-dimensional ball pit of billions of molecules bouncing off of each other from very short distances away, millimeters or even micrometers or nanometers, away from each other in our entire environment, and we can see through it. That's how small these molecules are. They're everywhere, but we can see right through them. And that constant collision and that constant speed that's happening is quenched by the opposing motion of other particles. Since they're going right here, it could be this, they're hitting together, bouncing off. It could be this, and they're all opposing. There's so many of them happening at the same time in opposite directions. We don't feel a thing, and we can walk through it easily. So that's a pretty cool way to think about it. Now, there is times where we can feel it, and sometimes it can kill you. When? When can it kill you? When is it bad? When can you feel it? You have a thought?
Like if you're falling from space, like wouldn't you then be able to feel it?
Okay. So when you're falling, you feel there's pressure on you, right? What's making that pressure? What does it feel like? Think of weather. Feels like
Like air.
wind, exactly. It feels like wind. So good thought, awesome. So with wind, what's your name?
Chelsea?
Chelsea. All right, great job, Chelsea. So wind, what is wind? So we can feel wind. We can go outside and feel it. Wind, all it is I'm not a meteorologist, but it is the movement, the coordinated movement of these gas molecules moving at that speed in the same direction, caused by a pressure gradient in the atmosphere, going from a high pressure gradient to a low pressure gradient, and they go towards the low pressure to balance it out. And we end up feeling that depending on how big the pressure gradient is of the air, we feel the force. If the bigger the gradient, the harder or the faster the wind is going to be. That's why in hurricanes and tornadoes, you have hundreds of miles per hour. But today it might be 10 miles an hour, which is a normal day. So all that is a coordination of wind. So what happens is when you feel wind, like let's say you're sitting outside, there's a little breeze of wind this way, a little breeze of wind this way, a little one this way. All that is the constant pressure gradient changes around you, which causes all the gas molecules in the air to go shoo, and then the pressure gradient changes over here, they go shoo, then it changes over here, then they move and they move and they move. That's all wind is. It's these like flowing of molecules in different directions caused by the pressure gradient. Mind blown, right? That's pretty cool. So you're gonna be like, you're gonna walk outside like you're high, you're like, whoa, like crazy, right? But that's the way it is. So that's pretty cool. And another thing is, I didn't see Eric, you said bump off. Yes, bump off is the right answer. Okay, so I can see, there's a lot of them, there's billions of them. I can see through them. But there is a point where I can't see through them. So let's say I'm in Hoboken, I'm looking over the Hudson River, I can see the city. But let's say I look towards the George Washington Bridge, and the bridge is in distance, and I don't really see it too well. And let's say there's no fog, or there's no precipitation in the way. The reason why you can't see it is not because your eyes don't work far enough, is because over that distance, the visibility decreases because the gas molecule layers are too many. and eventually maybe 10 miles or so, I think 10 miles is the maximum visibility when it's clear, that's when the gas molecules stack up enough to where it actually blocks our vision. So we do see them, but over long distances, when they compile, we see them. So yeah, that's crazy. Okay, we're almost done with time. Where's my phone? Yeah, whatever. Okay, so the last thing we're gonna do is mixtures. So there are two types of mixtures. There are, well, mixtures and pure substances. So there's two types of mixtures. There is homogeneous mixtures, which mean they have the same makeup throughout, the same uniform distribution of particles, right? So a great example of a homogeneous mixture would be salt water or sugar water when they're fully dissolved. So if you take one sip of sugar water, it'll be the same as the second sip. You'll get approximately the same number of sugar molecules in your body. So that's a homogeneous mixture. A heterogeneous mixture, they have visibly distinguishable parts. So I'm starving right now. I'm thinking of a sandwich. So you can take one piece of it. It could be bread. It could be the meat or whatever. A salad is a great heterogeneous mixture. Let's say sand and water, perfect one, because sand doesn't dissolve in water. So that's where they have difference throughout, a different uniformity throughout. So if you take multiple samples, the samples will be different.
What would oil and water be considered?
Good question. And that will be heterogeneous because oil and water are not what we call miscible in each other, meaning they don't mix together. And the reason why is because of polarity. So we'll be talking about that in another chapter. But polarity is basically the types of forces that are holding the water molecules together is different than the types of forces that are holding the oil molecules together. Since they're different, they can't mix. So that's why they don't mix. And they make two layers, like oil and vinegar too. So yeah, good question. Any other questions about these mixtures before we get to the substances? No? All right. So the next thing is pure substances on the bottom here. So a pure substance has a constant composition. It's a homogeneous mixture, but it's not a mixture at all. It's just a homogeneous substance. An example of a pure substance could be aluminum foil. You can write these down. Yeah, I don't know why they're not in the notes, but you can write them down. So pure substance could be aluminum foil. It could be pure water. It's just purely water, H2O. They're chemically bound together, but that's all the substance is. They're just of that compound. Could be a block of iron. That's a pure substance. So yeah, pure substance. Okay. Next and last thing. Oh, this is pure substance. Okay. I knew I had notes on it. Is physical change. Is your chemical change also? What is your chemical? Fine. Okay. So why is there not many notes on physical and chemical change? Okay, fine. So physical change, there's two types of changes from these types of substances or mixtures. There is a physical change or a chemical change. So a physical change is basically a change in which the chemical composition does not change. So if you rip a piece of paper in half, each side is still paper, still carbon. If you, I don't know, if you melt water, if you melt ice, it's still H2O in the ice, H2O in the water. So physical changes could be summed up as a change in shape or state. So by shape, I mean the shape, and by state, I mean solid, liquid, gas. And then we'll talk about chemical changes real quick. So chemical changes change or make new substances. Examples, you'll have burning, not burning, not burring, burning. You'll have tarnishing. You'll have rusting. And that's it. So that's the keywords for it. Baking, even baking. So examples of chemical changes, if you burn a log, you'll have ashes, you'll have H2O and CO2 from combustion. You can't put those back together, and those are different substances than the log. So that's a chemical change. Rusting, it is a chemical change of the iron that turns it into iron oxide, an oxidation. That is a chemical change. So chemical changes happen when you change the substance into something new. Physical changes is when you don't. So another thing is a question you could ask yourself when you're dealing with, oh, is this physical or chemical? You could say, can I undo it? If you can undo the process, such as melting ice, then it's physical. If you can't undo it, like baking a cake, then it's chemical. So, yeah. All right, any questions on that? I know I'm going through this stuff kind of quickly, but it's just the end. No? No? Online? You guys are good? And then here's compound and element. So these are the pure substances. I think those slides were out of order for some reason. I'm not sure why. I gotta move the chat. Okay, so the last thing, we went over the material. So this is a good slide for studying. This is a good slide. So here. So I made this resource. So this, everyone listen up. So you notice a lot of the stuff today was tidbits of information that there's a lot of it. You might forget the tidbits of information, especially when we go from chapters 1, 2, and 3, and you have a test on it the week after that. So I made this resource. It's actually an Instagram-based resource because I know everyone is into Instagram, and I made this resource called Crash Chem. So you can just Google it. You can Google Crash Chem, and I'll come up, and you can put it on Instagram. You can follow the hashtag. There it is. Hashtag Crash Chem. If you don't want me to see your Instagram, which I totally get it, that's weird. I'm a professor, but I won't follow you back, by the way, at least not yet, till the end of the semester. So you can put in hashtag Crash Chem, and that'll be a good resource. I'll tell you what it is. I'll show it to you. I'm gonna stop the recording.